Yeah. So the question was saying that on combustion analysis of some amount of decabrom. How much was what was the figure? Some milligrams.
Yeah.
Just tell me how many milligrams of decabrom?
1 second.
Yeah.
31.47.
31.472 milligram
Yeah.
of decabrom. We got some milligrams of carbon dioxide, right? How
Yeah.
many? 1.444.
Yeah.
1.444 milligrams of CO2. And then the question is asking whether the formula of decabrom is this or this, right?
Yeah.
So, okay. So basically, we have to guess which one will be the formula. So the key point here to understand is combustion analysis. Means basically you're burning something, right? Combustion means burning. So, and generally burning happens when you react things with oxygen, right? So the reaction will be D. I'll abbreviate this as say D. D plus O2 will give CO2 plus something. I don't know, right? And if the formula is C12Br10, C12Br10, and C12Br10 plus O2 should give on burning CO2. How many CO2? 6 CO2. Wait, no, not 6, 12. 12 CO2 plus 5 bromine molecules, and this is 12 O2, right? This should be the reaction if this is the formula, right? So the question says that how much of it we got was 1.444 milligram, and we used these many milligrams here, right? So that should give us a hint that if these many milligrams were used, so how many moles of CO2 were formed? 1.444 divided by 12. This is in millimoles, right? Because this was not in grams, this was in milligrams, right?
Yeah.
Correct. So millimoles of CO2 were formed. So, okay, not 12 divided by 44, right? 44 is the atomic
Yeah.
weight for it, no? So
Yeah.
by 44 millimoles, and these many millimoles are formed, then how many millimoles of decabrom should have been there? 1/12, right? Because
Yeah.
1 mole gives 12. So this many millimoles, that means the number of millimoles of this are this many by 44 by 12 millimoles, right? So that apparently that weighs 31.472 grams, right? So if let's check 1.444 by 44.44 into 12 millimoles into decabrom. The if the formula is this, then the weight should be 12. 12 are 144 plus 10 80 800 to 944. This many milligrams should have been there. When you do the calculation, it turns out to not be 31.472. Okay, it turns out to not add up to that. This calculation is not equal to this. So that means this formula cannot be right. This is wrong. You understand? So the only point here to worry about is the weight of CO2 that is released gives us the moles of CO2. The moles of CO2 that is released gives us the moles of decabrom. From the moles of decabrom and the weight given, we should get a molar weight, molar mass, which should match, but it doesn't match this formula. So this is going to be wrong. So it must be this. Okay. Everyone understood what happened?
Yeah.
So
Okay. So any other questions in stoichiometry that you want to discuss? Anything?
No.
If it is all right, then we'll move on to atomic structure. Otherwise, we'll discuss it. Any question? So,
actually, 3.116.
okay,
The B part, I'm not really sure about it.
okay. Also, you should also attempt chapter 4 questions, by the way, right? It's not just chapter 3. Uh, right? Chapter 4 will involve all of these redox reactions, and we learned last week the balancing of redox reactions, right?
Yeah.
So make sure that you don't miss out on chapter 4. So I'm expecting chapter 3 and chapter 4 to be covered by you guys, and you can ask me doubts whenever, right? So 3.116 part B. Okay. So 3.116 is basically saying the estimated concentration of gold in the oceans is 1 into 10 power minus 11 gram per ml. Express this in mole per liter. That is obvious, right? Correct.
Yeah.
Okay. So wait 1 second. 116. It is given 10 power minus 11 gram per ml. 10 power minus 11 grams per ml of gold in the ocean. So that means moles of gold will be, gold mass is 179 or 180, I think, right?
Yeah.
So you divide by 179, no, for sure, or 197. No, I'm not sure. So you can look at the periodic table and find out whatever it is, right? 1 second, let me just check. Gold
197.
197, no?
Yeah.
Okay. Okay. So you divide it by 197, that will give you moles per ml, right? So that will be moles per ml. So question is asking just that calculation. It's asking mole per liter. So multiply by 1000 to make it liter. So it becomes 10 power minus 8 by 197 mole per liter, right? That is part A. Part B is assuming that the volume of the oceans is this much. Okay, that is obvious, no? Why is this a problem? Volume of the ocean is given, then this is the concentration of gold, no? Akhil, what, is there a problem? Volume of the ocean is given, no? So concentration of gold is known, then you just multiply, right? Amount of dissolved gold in grams, 1.3 into 10 power 21 liters. So you just multiply by, you don't even need to convert it to this part. You have to multiply just by the 10 power minus 8 gram per liter. So this becomes 1.3 into 10 power 13 grams. So actually, you can say that almost 1.3 into 10 power 10 kilograms of gold. So 13 billion kgs of gold, oh my god, is dissolved. You understand?
Okay. Yeah.
That's it, right? Like this is quite easy, right?
Yeah.
Is there any problem? So this section is about this molarity and all. So you should be able to handle it. Any other questions? How far have you guys reached? Last week you guys were busy with the atomic structure stuff. Yeah, you did not have time to do this.
Done with stoichiometry, but I can do next week.
So make sure that chapter 3 and end of chapter problems, including the multi-concept problems, and same goes for chapter 4. Maybe take one more week and do it, okay? Don't delay it beyond the point, because anyway in Allen they will start mole concept and all soon, right?
Yeah.
So the next chapter, what is, has any of the teachers told you what is the next chapter in Allen? Nobody knows, huh?
Yeah.
Okay. So anyway, they have to do mole concept soon. So chapter 4, also the same thing. Make sure that you take the next week and do that, because it will reinforce whatever we have learned so far. Chapter 4, I hope nobody has forgotten how to balance redox reaction. Balancing of redox reactions we had learned. That is a crucial thing to know. Akhil,
Yeah.
you remember, right?
Yeah.
Okay. Bhavesh and all of you are familiar with that stuff, right?
Yeah.
Okay. So make sure that you practice problems. I don't want to spend too much time on it right now, because anyway, unless you do the questions, you will come back with doubts only then. So do that and get back to me during the week or next class. Okay. And what I will start is atomic structure then. Okay. So atomic structure, someone was saying there are too many formulas. Who was saying that?
Me.
Oh, too many formulas. Okay. But actually, it's a very logical chapter, not too many formulas. So first thing that you need to understand is light. Okay. What is light? Light can behave as a wave and as a particle. So actually, what I want you guys to understand is that light is what it is. We are unable to describe it in English. English words are not sufficient. You understand what I'm saying? Do you have a sense of what I'm saying, or should I elaborate? Huh? Someone try to guess what I say, what I mean by this. What do I mean? What am I saying?
We can't exactly define.
So basically, in English, we have understood wave to mean something, right? Wave is a word that means something, right, for us, right?
Yeah.
And particle is another word that means something else, right? So by particle, I start thinking of points and some masses, and these are the associations that I have in my head about particles, right? They have a fixed position and stuff, right? Correct. And when I think of waves, I begin to think about something being transferred, some energy or something being transferred. Energy is being transmitted through some space, right? No fixed location, right? So a wave doesn't have a position, right? You cannot say that a wave is this point, right? A wave is distributed over some space, right? Correct. So these ideas are old ideas, and we have assigned meanings to these words, but light doesn't care what humans think it should be, right? Like nature doesn't care what we say it is, right? It is what it is. Now we are trying to describe light. The problem is that it is something more complicated. It is more complex than either being a wave. It does not fit into these two boxes nicely. Okay. You understand? It is neither this nor this. It is something complicated. Okay. So that is what I mean. So when physicists understood quantum mechanics, they figured out that light behaves as both, depending on the experiment that you are performing, depending on which experiment you perform. So for example, if you do there will be something called Young's double slit experiment, which you learn in physics. Young's double slit experiment. This was done in 1801, which convincingly tells you that light behaves as a wave. Light behaves as a wave. Like the first idea of light was by Newton, and he said that light is a set of particles that travel in a straight line. Newton's proposal was light is a set of particles travels in a straight line. Okay, rectilinear propagation of light. You've heard of that, right?
Yeah.
That was in the 1660s. That was when Newton thought that light is a set of particles, because it is traveling in straight line, so it is being blocked by something, so must be some set of particles that are moving, right? So that was in 1660s. Then Newton said something, so people accepted it. Then 1801, some people started doubting. Thomas Young did an experiment where light was behaving as a wave. It was bending around corners. Then this is interference of light, and there is also something called diffraction of light. Light bends around corners. So in the 1800s, many experiments were performed, and almost everyone was convinced that light is a wave. Okay, and Newton was wrong. People thought that okay, Newton was wrong here, and light behaves as a wave. So many experiments have confirmed it. Okay, and we also know that light has a particular wavelength and whatnot, right? And it splits into different colors and all of that prism stuff, right? So by 1880s and all, there was common consensus that light is a wave. Okay, and Newton was wrong. But then Einstein came along in 1905. In 1880s, people observed something called photoelectric effect, and photoelectric effect was explained in 1905 in a paper by Einstein, and this again brought it back full circle, and now photoelectric effect cannot be explained by wave theory. Okay, can't be explained by wave theory. So in this case, again, light is behaving like a particle now. Particle. So photons of light have to be used. Only if you understand light as photons will you be able to explain photoelectric effect. Fine. So now there is a huge problem because sometimes it is behaving like a wave and sometimes like a particle. The thing is that by the 1930s and all, people had figured out quantum mechanics, and then people understood that it depends on the experiment. Okay, the nature of light, what you will observe, depends on what experiment is being performed. Okay, so it is something much more complicated, and we will not get into details of what it is. I mean, there is a set field called quantum chromodynamics or quantum electrodynamics. Basically, this was by Richard Feynman. Richard Feynman was the guy, and he sort of figured it out. And eventually, many people contributed. And light is something much more complicated. We will not get into that. But what we will understand here, the beginning of this atomic structure, understanding of atomic structure comes from this photoelectric effect, where we understood light to be a set of photons, right? Now, quickly, 5 minutes, photoelectric effect. Can someone tell me what it is? Photoelectric effect. This must have been discussed in Alan in some class, right?
Correct. Cathode, diode.
So, what is happening? There is a metal, right? And light is coming, right? And light strikes the metal, and then some electrons are ejected.
Yeah.
And the electrons are ejected with some V, some speed, maybe some kinetic energy they have, right? Correct.
Yeah.
And what the observations that were seen were that light has to be less than some particular threshold wavelength, right? Only then will you see photoelectrons. Only then you observe photoelectrons. Okay. No matter what you do, suppose you take light which is of longer wavelength, right? Longer wavelength means lesser energy, right?
Yeah.
So one thing that you should know is light energy is hc by lambda, which is equal to h nu, which is h into v, frequency, right? This is the formula for energy of light. And now, if you have light of lower than a threshold wavelength, that means higher than a certain amount of energy, right? Correct.
Yeah.
If light of energy higher than that is striking, only then do you observe photoelectrons. Otherwise, no electrons are emitted, okay, from the metal. And no matter, so this part, we should elaborate a little bit on this, because assume that you have the threshold wavelength is suppose 500 nanometers, suppose, right? So if you take wavelength of 490 nanometer, then you see photoelectrons. You see photoelectrons, correct?
Yeah.
Yeah.
If you shine 490 nanometer light, you will see photoelectrons coming out. But if you shine 510 nanometer, no matter what you do, you will not see electrons. Okay. So here the key point where wave theory failed was that I can take a very bright source of light, like a very highly intense torch or something, right? Like huge torch with high intensity, very bright source of light, and make sure that it has wavelength 510. So no matter how bright you shine the light, right, still zero for electrons are emitted. Okay. So intensity of light, no matter how intense that light beam is, if it has wavelength above 500, it will not be able to eject even one electron. Okay. And here, even if you take very faint light, like a very small pencil light or torch light, very tiny faint intensity, low intensity light, but if its frequency is 490 nm, electrons will be emitted.
Yeah.
You understand the difference? So according to wave theory, if wave theory was correct, intensity, high intensity means high energy you are supplying. Okay. High intensity light beam will have high energy according to wave theory, but then why are no electrons coming out? That doesn't make any sense, right?
Yeah.
And so wave theory is not able to explain this, why high intensity beam does not emit any electrons and low intensity beam is able to emit electrons. So the only way to understand it is in terms of photons of light. So packets of light are coming. Now HCV, in HCV volume 2, HCV volume 2, there is a chapter on photoelectric effect where he explains very nicely through a nice example why this photoelectric effect is an example of particle theory of light. He says that suppose you have a field, okay? Suppose you have a field of plants. There are some plants here, okay? And you are trying to water this field, okay? You are trying to water this field, right? So there are two ways in which you can water the field, okay? One way is to uniformly sprinkle water throughout, right? Like sprinkle water throughout the thing and hope that sprinkle water throughout, okay? And hope that each plant gets the amount that it needs, right? Correct. You could also water this field by throwing plastic pouches of water which on contact they break and all the water is spilled into that portion, right? You are throwing pouches now randomly. You understand? So there's a difference between this uniform continuous sprinkling of water as opposed to throwing pouches, right? So the difference is that this is going to be gradually, all the water will be collected, like each plant will get its own share, but it will be distributed over the whole place, right? The water will be distributed over the whole field, but so that is like a wave theory understanding. So intensity transmits energy. The higher the intensity, the more the energy. And this is like a particle understanding of light, where each photon carries this much energy. If this pouch lands on this plant, right, then plant gets a lot of water suddenly. If it doesn't land on this plant, no water, right? You understand? So that is how light is. Like photons are carrying some amount of energy. If it strikes an atom here with h nu greater than the work function is the amount that is needed to hold the electrons inside the metal, right? If your h mu or hc by lambda is greater than the work function, then immediately electron will be ejected because the whole of the water is falling on this plant, right? In this case. So either you hit, it's like a hit or miss situation. If you hit, then if the packet has enough water to eject an electron, it will eject, no matter how few photons come. So in the particle theory of light, what we understand by intensity is number of photons, okay? So even if only 10 photons come here, right? So low intensity, 10 photons. If those 10 photons have enough energy to eject electrons and they strike the atoms, then 10 electrons will come out definitely, okay? Even if your billions of photons are there, billions of photons, but none of the photons are strong enough like none of the photons have energy enough to eject an electron, then 0 electrons will come out. You understand?
Yeah.
Yeah.
Okay.
Yeah.
So what we have is an equation. What we have is an equation: energy incident will be equal to work function of the metal, work function plus energy of photoelectron that comes out. Energy of photoelectron that comes out. Don't confuse this photoelectron with the photon, right? This is the incident energy, photons. And this is photoelectrons kinetic energy. Kinetic energy, so half mv square that comes out plus work function should be equal to hc by lambda. This is the defining equation of photoelectric effect, right? So this hc by lambda is incident energy. This is balancing energies, the energy conservation principle. So work function is another energy. Now work function is what? Basically, work function is how much energy is required to extract an electron from the metal. So basically, how much force is holding the electron inside the metal. So work function will be different for different metals. Some metals might hold their electrons more strongly. Some metals might not hold their electrons so strongly, right? Correct. So this is a constant that depends on the material, and the threshold wavelength is decided by this constant. So what will happen is kinetic energy of the electron becomes hc by lambda minus work function, right? So the maximum value of kinetic energy, this is the maximum value of kinetic energy, hc by lambda minus work function. So this is assuming that once a wave has struck and electron has come out, there is no loss of energy in the process. You understand? So this much energy came, work function was needed to eject an electron. So difference becomes the kinetic energy, right? It could be the case that many of the electrons that are emitted will not show this much energy, right? They could be less than this, right? Because electrons could, while coming out of the metal, they could hit each other, lose some energy, right? There could be many arbitrary things that can happen, correct?
Yeah.
So this is the maximum possible energy of emitted electron. Now, sometimes the electron could be emitted with almost zero velocity, right? Like they have just about crossed the metal and nothing. They don't have any other energy, right? So you can say that kinetic energy output is zero. So that means hc by lambda is equal to work function in that case, right?
Yeah.
Correct. So this is photoelectric effect. Now what we need to understand is atomic spectra. What is atomic spectra? What is this atomic spectra and why are we talking about it? In light of what you have learned in atomic structure, why do you need to understand atomic spectra? And first of all, what is it? Someone explain. Rishi, tell me if you know something.
So basically, it's like when you pass light through a solution of some atom.
Solution.
So, like a mixture. Yeah.
Okay. Some atom, some substance,
Yeah.
some material.
Yeah.
Wait, you pass light through the material, huh? Okay.
Okay. So the atoms will absorb some specific wavelengths of light,
Okay.
while
That
the
is
others will just
okay. So that what you're talking about is called absorption spectra.
and there's no other emission.
Emission spectra. Let's talk about the slightly more common scenario. Emission spectra. What is that?
So
Emission spectra.
that's like if there are some atoms which are excited and the electrons are in a higher level of energy,
Uh-huh.
When they move back to the lower levels, they'll emit a photon of some.
Correct. So, do you know why people were studying this? What was happening? Like the background, like what happened? So, there's atoms. If you heat it, right? If you heat some substance, so for example, sodium, you took a lump of sodium and heated it, then people saw that okay, sodium is glowing. After some time, it will start glowing with some certain color. Maybe it glows red, and after that it glows something else, and eventually it glows white, and so on, right? When you keep heating it, right? And people observed that the emitted wavelengths of light that were being emitted by that sodium is following a certain sequence of wavelengths. Like what they saw was sodium is only emitting a certain set of lines. So suppose this is 312 nanometer, this is 450 nanometer, this is 600 nanometer, this is 718 nanometer, whatever. I'm making up some numbers, right? So sodium was emitting light only of these particular wavelengths. Okay.
Yeah.
Okay. And when they did the experiment for something else, the lines were different. The different wavelengths came. Okay. So the obvious question was why these particular numbers, and why is it different for different materials, and so on, right? Like there are many unanswered questions here. You understand? Both of you are getting the problem. Like why in 1800s, if you said to someone that okay, sodium emits only these particular wavelengths when it is heated, they would be asking why these numbers, what is special about these numbers, why not some other numbers, why not 451, right?
Yeah.
Correct.
Yeah.
Why not 599 or whatever, right? What is up with this arbitrary numbers, right? And when you saw potassium, it was some different set of numbers, and when you saw hydrogen, it was some different set of numbers. So every element sort of had its own fingerprint, had its own signature set of lines. Okay.
Yeah.
And no matter what you did, no matter which type of experiment you did, what temperature you raised, whatever happened, it was always, sodium was always showing these numbers only. Okay. So this is a lot of like mysterious stuff going on, right? Like now you know why that is, right? Can you explain? Because you've done atomic structure, now you know why that is, correct? Because when you heat some substance, the atoms gain energy, so they go to higher energy levels, right? And once they go to higher energy levels, they are in their excited state. Now suppose you are at this level, you can fall down to this level, you can fall down to this level, you can fall down to this level, the electron can come back to its lower level, and each transition releases a photon, right? Each transition releases a photon, and because the transitions have fixed energy levels, the photons will have fixed wavelengths and frequencies, right?
Yeah.
And
Yeah.
because each element's atoms energy levels are different and predefined, like fixed. Like it is not like sodium, one atom of sodium will take, it will have different energy levels from another atom, right? So sodium's energy levels are fixed, so only fixed lines can come in sodium energy spectra transitions, right?
Yeah.
And something else is, so if it is sodium and if you get hydrogen, the energy levels for hydrogen are different values. Okay. So only those transition lines will show up in hydrogen spectra, right? So that is
Yeah.
emission spectra. Absorption spectra is the reverse. You go from here to here, or here to here, or here to here, on absorbing some energy from some photon, right? Correct.
Yeah.
Yeah.
Everybody is clear on this, right? It's nothing very complicated. It's just that each atom has some predefined energy levels, and only those energy levels, the gap between them matters in the photon's wavelength and frequency, right? Correct.
So like this process kind of works like a cycle.
Like a cycle, as in, what do you mean?
I mean, when it absorbs, it goes to a higher energy level, and it loses, and it comes back to a lower energy level. So that keeps happening, right?
So if light is falling through a material, right? Light of suppose 100 different wavelengths of light are coming, right? Correct. Suppose 100 different wavelengths are coming, or 600 different wavelengths. Visible light is being is shining on something, right? 300 to 900, right? Actually, there are how many wavelengths in between? Infinite, right? Infinite wavelengths here, right?
Okay.
You understand? No? Only the integers are not necessary, right? It can be any wavelength, right? So infinite wavelengths are falling on something, but the sodium atom has some energy level here, E naught something, E1 something, E2 something, E4 something, E3 something, right? Now, only the electron cannot exist in any intermediate place, okay? It can only exist in this level or this level or this level and so on, right?
Yeah.
So when light falls, it will be able to accept a photon only if the photon corresponds to this gap or this gap or this gap, right?
Yeah.
Correct. So
Yeah.
only those wavelengths will be absorbed, other wavelengths will not be affected, and it will just pass through. So the outgoing light will not have those particular wavelengths. They will be absorbed. You
Yeah.
understand? So the atom does not have a lot of freedom in what it can absorb or what it can emit. It can only do it for the energy levels where the electron can only exist in these levels, right? So once the atom is excited, after that it can go back to its ground state. So you will see the same spectra lines coming out in the emission spectrum. Emission spectrum will look the same gaps, right? The same gaps that appeared here will show up in the emission spectrum also, right? So yeah, it is like a cycle sort of, because when it falls back, it will be the same thing, right? Okay, so this is atomic spectra. Now there is a equation. So there was a school teacher in Switzerland called Johann Balmer. Johann Balmer, and what he did, he took a few numbers. These were numbers given to him by some colleague, and some numbers were given to him like this. And the colleague said that these are wavelengths of some hydrogen spectra or something. Okay, wavelengths that we see in hydrogen spectra, right? And then and the scientist who was doing the hydrogen spectra, he was like, yeah, I can't find any pattern here. See if you can figure something out, right? I can't find any patterns. This was 1870s or 80s. People did not know what to make of these numbers. This guy figured out this formula. Some number 1 by 2 square minus 1 by m square, and m can be 3, 4, 5, 6, and it suddenly started fitting. Lambda can be put in this is a constant, and this suddenly started fitting. So he took some, so imagine, like, this takes a lot of ingenuity, you know, to take three numbers and find a formula, right?
Yeah.
Like, that was quite smart. So this guy figured out this formula. As soon as he came up with the formula, people all over all the scientists figured out, okay, now we can explain all the different series by similar formulas.